All right, today's lesson has to do with the acid and basic properties of salts. So the first thing we have to realize is the relationship between Ka and Kb. So Ka is the acid dissociation constant, Kb is the base dissociation constant, and how nice there's a relationship that if you multiply those two together, you get Kw. So for water at 25 degrees C, they will always, when we multiply both of them, they will always equal 1 times 10 to the negative fourth. All right, that's going to become important because when we look at salts, which are just ionic compounds, we are going to have to find the conjugate acid or conjugate base, Ka or Kb. Those are not going to be tabulated for us. Only the Kas and Kbs of a weak acid or a weak base are in the table. So to find the cation or anion, which are the conjugate acids and conjugate bases, we will have to calculate the Ka or Kb. All right, so let's look at a particular salt. Let's look at, let's look at several. Let's look at NaCl. Let's look at NaNO3. And let's look at NaNO2 and NH4Cl. All of those are salts. All of those are ionic compounds, so they're considered salts. And what we have to look at is the pieces. When these things go into water, they're dissolved. And when they dissolve, they dissociate. So they separate into their ions. So NaCl separates into Na plus and Cl minus. NaNO3 separates into Na plus and NO3 minus. Na plus, NO2 minus. And NH4 and Cl minus, NH4 plus and Cl minus. Okay, these cations and anions, we're going to kind of look at them from as if they came from a weak acid or a strong base. Because remember, if you have an acid plus a base in a neutralization reaction, it'll make water plus a salt. So the salt's what we're looking at. So we're kind of going to go back and figure out whether it came from a strong acid or a weak acid or in a strong base or a weak base. Okay, so if you think about NaCl being the salt, what acid and base had to come together to make NaCl? Well, the acid had to be HCl and the base had to be NaOH, right? We know, because we have memorized, that HCl is a strong acid and NaOH is a strong base. So cations that came from strong acids do not affect the pH. Okay, because remember, if they're really strong acids, then the conjugate base is very, very weak. So it's so weak that it's not going to affect the pH. Anions from strong bases, which is what Cl is, right? Yeah. Did I say it backwards? I just said it backwards. The cations, the Na, from a strong base won't affect the pH. The anions from a strong acid also will not affect the pH. So the pH of NaCl in solution, a saltwater solution, would have a pH of 7. It would still be neutral. Okay, what about NaNO3? Well, we've already decided that Na plus came from NaOH, which is a strong base. So this weak conjugate acid is too weak to affect the pH. So that one won't affect the pH. And NO3 minus came from HNO3, which would again be a strong acid. So this one won't affect the pH. So the pH would be 7. All right, but now let's look at NaNO2. If we think about the Na plus came from NaOH, which is a strong base, so the conjugate acid Na plus is not going to affect the pH. But what about the HNO2? It came from HNO2. NO2, not NO3. NO2, which is a weak acid. So the weak acid has a fairly strong conjugate base. So this is a conjugate base of HNO2. This one will affect the pH, and because it's functioning as a base, a conjugate base, this salt will be basic, and we'll figure out how to calculate the pH in a minute. All right, so that salt would be basic. NH4Cl, the NH4 really came from NH3, which is a weak base. So this conjugate acid is fairly strong, or strong enough to affect the pH. All right, and then the chlorine happens to be from HCl, which is a strong acid, so it won't affect the pH. So this particular salt in solution would produce an acidic solution. What happens, and there are times you can have cations and anions that both affect the pH. Let's look at one of those. What if we had the NH4 and the NO2 together? How would we decide which one affects the pH? They both do, so one has to be affecting it more than the other. We would have to find their Kas and Kbs and see which one's bigger. So NH4 plus came from NH3, which is a weak base. So this one is a conjugate acid. NO2 came from HNO2, which is a weak acid. So this is a conjugate base. Both of these conjugates are able to affect the pH, but we have to decide which one. Basically, you're going to go look up the Kb for NH3. The Kb's, these are what's tabulated. The Kb for this and the Ka for that. That's what's in the table in Appendix D. That's not what we're worried about. We need the Ka for that and the Kb for this. So if we go look up the Kb of NH3, which, let me see if I have it handy, because I just kind of made this problem up. The Kb for NH3, I think, is 1.8 times 10 to the minus fifth. So the Ka of NH4 plus would be 1 times 10 to the minus 14th divided by that 1.8 times 10 to the negative fifth, which would be 5.56 times 10 to the negative 10th. Okay, that equation right there is me rearranging Ka times Kb equals Kw. That's really what that is. All right, and then if you go do it for the other one, you can go look up Ka for HNO2, and I don't think I have that one handy. So I'll let you do that one. I'll let you go look up the Ka for HNO2, and then you'll have to calculate Kb for NO2 minus, which would be 1 times 10 to the minus 14th divided by whatever you looked up for Ka for HNO2. And then basically you will compare this Kb with this Ka and figure out which one was larger. I don't know off the top of my head. So whichever one was bigger would dictate the pH, and then that's what you would do your equilibrium with. And we're going to do some other examples. I just kind of made that one up as I was going. But I think you get the point. All right, let's look at the example from your notes. I'm on page, I think it's like page 9 of your notes or so. Let me flip the page. So page 9 of your notes at the bottom. There's an example problem that says sample problem 14.21, and it says predict whether an aqueous solution of each of these following salts would be acidic, basic, or neutral. And the first one they give you is NH4. Oh, my pen didn't write. NH4, C2H3O2, and then they give you B is NH4, Cn, and then C is Al2SO4, 3. All right, so the salts, you got to divide them up into their parts, right? The cation and the anion. So NH4 plus, actually we have already calculated, that's going to be functioning as a conjugate acid, right? Of a weak base, right? Because it came from NH3. And the C2H3O2 is the acetate, which is going to be the conjugate base of the weak acid, acetic acid. So you're going to need to know the Ka for the NH4 plus, and you're going to need to know the Kb for the acetate ion. Okay, so we've already found the NH4 plus on the previous slide. Yeah, 5.56 times 10 to the negative 10th. That will be the Ka for the NH4 plus. And the Kb for the acetate, we will have to go look up. And this one I did do. If you go look up the Ka for acetic acid, the Ka for acetic acid, and that's in Appendix D, it's 1.8 times 10 to the negative 5th. So to find the Kb, it's 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th. And we're going to get the exact same number. We're going to get 5.56 times 10 to the negative 10th. So both of these are exactly the same. So neither one will affect the pH, or they'll affect the pH the same. So this one will still be pH of 7 or neutral. Okay, the next one, the NH4 plus, we already know Ka for NH4 plus. It's 5.56 times 10 to the minus 10th. But we got to find the Kb for the Cn minus. So it's 1 times 10 to the minus 14th divided by the Ka of HCN, which we'll have to go look up. So 1 times 10 to the minus 14th over, I think I have this one, 4.9 times 10 to the minus 10th. So the Kb of Cn minus will be 2.04 times 10 to the minus 5th. So this one is significantly bigger, so this will be basic. Now when we get down to this one, we have to know the Ka of Al3 plus. That one's a little weird, because if you go look in the table in Appendix D, there is not a Kb for AlOH3. It's not listed, but there are values for Ka for metals, and typically the higher the charge on the metal, the stronger acid this ion will be. But there is a table for this, and it's table 16.6 on page 703. Anyway, and if you go look up the Ka for that, it's 1.4 times 10 to the negative 5th. And even if you couldn't look that up, if you start to look at the SO4 2 minus, right? We need the Kb for SO4 2 minus. We have to go look up the Ka, but when we start to look at the Ka, I should have put a copy of it on here, but I didn't. If you look at H2SO4, you'll see a Ka1 just says strong acid, and then Ka2 is 1.2 times 10 to the minus second. Well, we need to use the Ka2 because remember, Ka1 is H2SO4 going to HSO4 minus with an H plus coming off, right? That's where Ka1, that's the reaction. Ka2 would be that HSO4 minus giving off an H plus and going to SO4 2 minus. This is the anion we have. So we need Ka2. So we're going to put 1.2 times 10 to the minus 2 and get 8.33 times 10 to the minus 13. So, oops, actually that one shouldn't be circled. That one's very, very small, much smaller than this one. So the Ka dictates, so this salt is acidic. Okay, and hopefully you're seeing the relationship that if this is technically a fairly strong weak acid, right? It has a fairly large Ka. And then the conjugate, right? This is the conjugate base is very weak, almost the same as water, because water is times 10 to the negative 14th. So hopefully you can see that inverse relationship there. All right, let's do one more example, because this one's like on your homework tonight. Actually, it's two more examples. I'm doing number 81 at the end of the chapter. And it basically says that you have a solution of sodium acetate, however you want to write acetate, and it has a pH of 9.7, and they want you to find what was the original molarity of the solution. Okay, so we're kind of working backwards on this one. If we know the pH, we know an H plus concentration. We also know a POH, so keep those things in mind. All right, but let's start with our little, steps for figuring these out. What are the major species in this solution? Well, that's a salt, so it divides up into Na plus, the acetate ion, and then we've got some water there. Which one of those is going to affect the pH of the solution? Well, it's not going to be the Na plus, right? Because that is it's a conjugate acid from NaOH, which is a strong base, so its conjugate acid is very weak and won't affect the pH. The acetate ion, on the other hand, came from acetic acid, which we already know is a weak acid, so this is a conjugate base that's probably affecting the pH. And then we know water is 1 times 10 to the minus 14th. So as long as we get something bigger for that conjugate base than water, then this is what will dictate the pH. And we already know from calculating it before, right? We've already found the Kb of the acetate ion. It was 5.5, yeah. 5.56 times 10 to the negative 10th. We already calculated that on one of the other problems. All right, so we know it's going to be basic. So the equilibrium that we are working with, write the equilibrium equation. The equilibrium that we're going to be working with, and it's basic, so remember to add the water. And then the water will donate the H, and you'll be left with hydroxide. So it does look like a basic. So this is kind of your equilibrium. This is your ice table, if you will. So if you want to see it in an ice table, you may be where you can see it without it. Ooh, not drawing very straight lines. All right, we don't care about the water. Remember, it's a pure liquid. And we don't know these initial, we know these are 0, but we don't know what this initial concentration is. That's basically what they're asking us to find. We do, however, know this number. We know the hydroxide concentration at equilibrium because we know the pH. So you can go from pH to H plus concentration and then to the OH minus. I tend to like to go from POH. So I know that the pH plus the POH equals 14. So the POH is going to be 14 minus the 9.7, which will be, if I can read my notes, 4.3. And I know that the POH equals the negative log of the OH minus concentration. So if I want to find the OH minus concentration, it's going to be the POH, oops, nope. It's going to be 10 to the minus POH. So that's going to be 10 to the minus 4.3, which comes out to be 5.01 times 10 to the minus fifth. So we know this concentration. And since this was X and this was X, we also know this concentration. What we don't know is this, right? And this is really minus the 5.01 times 10 to the minus fifth, but we always assume that K is so small, which it is a very small K, that this isn't really going to affect H. So our KB expression is the concentration of the acetate times the hydroxide over, oh, that was acetic acid times hydroxide over the acetate ion. So we have 5.01 times 10 to the negative fifth. This will end up being squared over X, and that's going to equal 5.56 times 10 to the minus 10th, which is our KB. So X is, when we solve for X, let me see where I found it. Oh, X ends up being 4.5. Well, that is the acetate concentration. So that should say 4.5 molar. Okay, so hopefully you can go that way. Now let's go the other way. This is number 79. And this question asks you to find the OH minus concentration and the pH of several solutions. So A, it wants you to find it of 0.1 NaBRO, and maybe we'll have enough room. And B is 0.08 molar NaHS. And then C, which I'm sure we'll have to do on another page, is a mixture of 0.1 molar NaNO2 and 0.2 molar CaNO2. Okay, all right, let's look at the first one. The first one's not too bad. What's in solution? Na plus, BRO minus, and water. We know by now that the sodium, the Na plus, is not going to affect the concentration. So the BRO minus is the only thing that can, and it happens to be the conjugate base of HBRO, okay, the hypobromous acid. And if I go look in Appendix D, the Ka for that is, oh my goodness, the Ka for that is 2.5 times 10 to the minus 9th. And so we have to find Kb because this is functioning as its conjugate base. So Kb is going to be 1 times 10 to the minus 14th over 2.5 times 10 to the minus 9th, which will come out to be 4 times 10 to the negative 6th. All right, so the equilibrium that we're working with is BRO minus plus H2O because it's functioning as a base. So to make HBRO plus OH minus, so Kb is going to equal the concentration of the HBRO times OH minus over BRO minus, and this becomes X squared if you put it in an ice table, and this was 0.1, and we're assuming the minus X doesn't matter. So 4 times 10 to the minus 6. When you solve that for x, you end up getting 6.32 times 10 to the minus 4th, and x is the OH minus concentration from your ice table. So then I find the POH, which is the negative log of that number. Oh my goodness. And the POH is 3.2, but they didn't ask us for the POH, they asked us for the pH. So the pH is 14 minus the 3.2, which is 10.8. So this and this, whoops, is the answer to A. All right, I'll do B on another page. B was 0.08 molar NaHS. All right, this one's a little funny because, and we didn't talk about it, I meant to before, but I forgot. We didn't talk about the amphoteric species. All right, here's the three things that could be in solution. We know that the Na plus is not going to affect the solution. The funny thing is HS is amphoteric. And that's because it can gain an H plus. It can gain an H plus and become H2S, or it can lose an H plus and become S2 minus. So it can either function as an acid or a base. So we are going to have to decide which way it's going to go, and that's going to be based on the Ka of one and the Kb of the other. So if it's amphoteric, all right, so let's just look at the H2S. All right, if HS is functioning as an acid, then it will drop an H plus and become S2 minus. And that is just the Ka2 of H2S. Okay, remember, H2S dissociates stepwise, right? So this would be Ka1, this would be Ka2 in the tables in Appendix D. So that looks exactly like that equation. So basically we just have to go look up Ka2 for H2S. And if you go look it up, it's 1 times 10 to the negative 19th, which is really, really small. Our other option, this is it working as an acid. So if it's basic, we have to add the water, and it will lose, well, it will gain, sorry, it will gain an H, and the hydroxide will come off. All right, so in this case, we have to know what its Kb is. Well, the Kb, it came from that H2S, so this has to be the Ka1 of H2S, which when you go look up that number right there, that's 9.5 times 10 to the negative 8th. So 1 times 10 to the minus 14th over 9.5 times 10 to the minus 8th will give us a Kb of 1.05 times 10 to the minus 7th. All right, so if you compare Ka to Kb, you can see that Kb is much larger than Ka. So although this is amphoteric and can do either one, it will function as a conjugate base. So this is the equilibrium that we are going to work off of, and we will use Kb for this particular thing. All right, so if you think about your ice table and have 0, 0, and the original concentration was 0.08, then Kb, which is 1.05 times 10 to the negative 7th, is going to equal the H2S times the OH minus over the HS minus, which these two are X from the ice table, and this is 0.08 minus x, and we're ignoring the minus x. When you solve for x squared, you get 8.42 times 10 to the minus 9th. And then take the square root, you get 9.2 times 10 to the minus 5th. Well, x is the OH minus concentration, right? If you need to see the ice table, then set it up. Right? And that's exactly what I plugged in down there. So you can see that X is the OH minus concentration, and then I do the same thing. The P of OH is the negative log of that number. And so the POH was 4.03. The pH is 14 minus that, which ends up being 9.96. So that and that are the answers to your questions. All right, and then in C, this is the last one we're going to do, and then you can work on your homework. C is a mixture of 0.1 molar, I forgot my molar, NaNO2 and 0.2 molar CaNO2. So if it's a mixture, then what's in solution? We have Na pluses, we have NO2 minuses, we have Ca2 pluses, we have some more NO2 minuses, and we have some water. Okay, the sodium we know won't affect the pH, neither will the calcium, because the calcium came from calcium hydroxide, which is a strong base, right? So then this conjugate acid is just like the Na+. It's too weak to affect the pH. So those two things won't. This, though, came from HNO2, which was a weak acid, so this is functioning as a conjugate base. Still functioning as a weak base, but strong enough to affect the pH. So as long as this Kb is higher than 1 times 10 to the negative 14th, then the solution will be basic. All right, so we need to find the Kb of the NO2 minus. So to find Kb of NO2 minus, you have to do 1 times 10 to the minus 14th over the Ka of HNO2, which I think, is this the one we didn't do? Let's see, I've got it somewhere. Okay, the Ka of the HNO2 is 4.5 times 10 to the minus 4th. So the Kb ends up being 2.22 times 10 to the negative 11th. All right, so we're going to need that, and I didn't write Kb there. That's Kb of the NO2 minus. All right, so let's write our equilibrium reaction. NO2 minus, it's functioning as a base, so I leave the water in. It's going to give me HNO2 plus OH minus. If you want to see the ice table, actually, we need to calculate that concentration because we have a mixture, right? It comes from the NaNO2 and the CaNO2 too. We don't really care about the water. This is 0, 0. This part we can fill in because we know this part. All right, so let's calculate the molarity that would be here. From the NaNO2, you're going to have 0.1 molar of this because there's one NO2 that comes off for every time this dissociates. So I have that concentration from the first one, and I have 0.4 molar NO2 minus from this one. It's 0.2 molar to begin with, but we have 2 of them, so 2 times 0.2. So altogether we have 0.5 molar NO2 minus. So this is 0.5 molar. So, whoops, minus x, so 0.5 molar minus x, and we're going to assume that that x doesn't matter. So 2.22 times 10 to the negative 11th, which is our Kb, is going to equal x squared over 0.5 molar. And when we solve for, we end up getting x squared equals 1.11 times 10 to the negative 11th. And then when we take the square root, x equals 3.3 times 10 to the minus 6th. This happens to be the hydroxide concentration, which is one of the things they wanted us to find. And the pOH is the negative log of that, which ends up being 5.5. So the pH is 14 minus the 5.5, which is 8.5. Somehow I have another number in there, 8.52. Okay, and this part. All right, that should be enough to help you with your homework. I would highly suggest reading this section and the next section because I didn't really go over the strengths of acids, but that one's pretty clear. Plus, I'll put some typed notes up that you can just read through and be able to figure that out for your homework. Have a good weekend.